everyone, it is Sridhar at E-shikshana. In this video, we'll discuss a few more sensors and transducers. So far, we have discussed about proximity sensor, pneumatic sensor, light sensor, tactile sensor, smart sensor, and fiber optic transducer. Before starting the other sensors and transducers, I'll suggest you to go through my previous video on these above mentioned sensors and transducers. The link is given in the description. In this video, we'll discuss on digital transducers, rotary variable differential transformers, RVDT, synchros and resolvers, induction potentiometers, and micro electromechanical systems. We'll start with the digital transducers. The output of a digital transducer is a discrete and may give frequency type of output or a digitally coded output for binary or some other type. The digital transducers ranges from frequency generation type of a transducer to a digital encoders. Alternatively, an instrument may be incorporated in an analog transducer and analog to digital converter, which is shown in the figure, giving a digital output. The advantages of digital transducers are: it is possible to obtain increased accuracy in pulse count. It becomes easy to use digital computers along with the transducer for data manipulation. There are economic advantages in presenting a digital data. It is easy to transmit digital signals without distortion and external noise. Since digital transducers, the output signals are not depend on the signal amplitudes. Frequency domain transducers. The following are the three types of frequency domain transducers: electromagnetic frequency domain transducer, opto-electric frequency domain transducer, vibrating string transducer. The output of these transducers is in the form of pulses or sinusoidal waveform, the frequency of which is measure of the amplitude of physical variable. First, we'll start with electromagnetic frequency domain transducer. The diagram shows an electromagnetic frequency transducer which can be employed for measurement of speed. It consists of permanent magnet on a solenoid. A gear of ferromagnetic material is mounted on a rotating shaft whose speed to be measured. As each gear tooth passes in front of the magnet, the gap length changes. Consequently, there is a change in flux density and a voltage pulse is induced in the coil. Pulse frequency equals speed n times the number of teeth t. The output is shown in the figure, which is a pulsated output. The pulse frequency is a measurement of the rotational speed. Next, we'll discuss on optoelectric frequency domain transducer. A figure shows the schematic arrangement of the transducer for linear motion, which consists of a light source and a lens. The arrangement includes a transparent scale with a grating. A light from the source passes through the scale and the slit and then falls on the photoelectric transducer. The slit width is such that a motion equal to the pitch of the grating produces one complete cycle of light and darkness at the photoelectric cell, and thus pulse output is obtained. From the number of pulses, the change in motion of the scale and the object attached to it can be determined. Another arrangement shows electric frequency domain transducer for measurement of rotational speed of shaft, which consists of a shaft which is coated with a half dark portion and half shiny portion. Every time the white or shiny portion of the shaft is in front of the light source, the reflected light falling on the photoelectric transducers gives an electric pulse output. The frequency of pulses is thus measure of the speed of rotation of the shaft. Vibrating string transducer. This type of transducer is essentially employed to measure the force applied to metal string, which is kept vibrating, the frequency of which is depend on the force applied. The natural frequency of the string is given by this equation, where F is a natural frequency of a string, L is the length of the string, P is the force applied, A is the cross section area of the string, rho is the mass density of the wire material. The arrangement is shown in the diagram, which consists of a fixed end, a metal string is stretched, and a electromagnetic vibration generator and the electromagnetic transducer connected with an amplifier. The vibrations are picked up by the electromagnetic transducer. The output of a transducer is amplified by the amplifier and then fed to an electromagnetic vibration generator, which maintains the string vibration at its natural frequency, F. The frequency F gets changed due to change in the magnetic force, P. The frequency is measured by the frequency counter and is measure of the force applied to a string. This transducer can be used for measurement of force and displacement. The vibrating diaphragm and cylinder type of transducers have been developed to measure the pressure. Next, we'll discuss on digital encoders. In contact type arrangement, there is a direct contact between the brushes and encoder disc. The disadvantage of such system is a wear of brushes and disc. There are two types of digital encoders discussed here: optical type encoder and magnetic type encoder. The first one is an optical type encoder. It is a non-contact recorder. The disc has a transparent and opaque areas corresponding to the conducting and non-conducting one respectively in the contact type encoding disc. A light source is used along with the slit and the photocells. The photocells corresponding to the particular track would produce an electric output. If the transparent portion is in front of the slit and the light source giving state on or logic 1, while no electric output from the cell would corresponding to off or logic 0 state. Next, the magnetic type encoder. It is also non-contact type encoder. This encoder uses the number of small toroidal magnets with coils around them. The area corresponding to the conducting and non-conducting ones in the contact type encoder disc form the non-magnetic and magnetic areas on the disc. The presence or absence of such areas is detected by coils which are in close proximity to each track on the disc. One of the coils in each toroidal magnet is energized with the frequency AC carrier signal. The toroidal is over a non-magnetic area of the encoder disc. A voltage due to transformer action is induced in the output coil state 1, while magnetic area would saturate the magnetic circuit and the output is very small, producing state 0. The signal on the output windings are demodulated to remove the high frequency carrier signal. Next, we'll discuss application as digital pressure transducer. At present, the digital transducer include the signal conditioning circuit associated with electronic circuitry within the body of the transducer itself. The various stages of the transducer are shown in diagram, which consist of a strain gauges, amplifier, analog to digital converter, output controller, and microprocessors. Overall construction can be taken out as a built-in signal processor and the measurement circuit. This part of the arrangement represents a transducer assembly with the physical quantity to be measured, and this part of the circuit represents a built-in signal processing consisting of a preamplifier, analog to digital converter, output process control with a microprocessor, and the defined electrical output can be directly connected to a digital display or modified given a direct output to 0 to plus or minus 5 volts or to 4 to 20 milliamps. Next, we'll discuss on Rotary Variable Differential Transformer. In short, we can call it as RVDT. So RVDTs are used for measurement of angular displacement. It converts the angular displacement into electrical signal. So the operating principle is similar to that of the LVDT. The construction and working of RVDT, so it consists of one primary and two secondary windings. The only difference is that the core is a cam shaped and the rotating inside the windings through its shaft. The core is rotated in clockwise and anti-clockwise direction with respect to null position. When the core is at null position, the voltage is zero because the voltage induced in both the secondary windings S1 and S2 are equal and in opposite directions. When any angular displacement is to be measured with respect to null position is applied to a shaft, a differential voltage gets developed across the secondary windings at the output. When the core is rotated in clockwise direction, the voltage gets increased. If the core is rotated in anti-clockwise direction, the voltage gets increases. The output voltage is increased in both the direction, but there is opposition with respect to each other according to the position of the shaft, clockwise and anti-clockwise directions. Next, we'll discuss on synchros and resolvers. So these are the class of AC electromechanical variable coupling transformer devices primarily employed for angular data transmission and computing systems. Next, we'll discuss on the synchros. The synchros act as a transmitters and resolvers act as a receivers. The construction of synchros is shown in the diagram. The basic electromagnetic structure of synchros consists of wire-wound rotor and wire-wound stator, concentrically arranged to give adjustable mutual coupling between the windings of two members. The rotor is wounded with a single phase concentrated winding and the stator is wounded with the three-phase distributed winding. The rotor is excited with an AC signal and by the transformer action between the rotor and the stator winding, the voltages are induced in the stator coil. The magnitude of these voltages depend on the angular position of the rotor with respect to the stator. And the diagram shows a typical practical setup in which the pair of synchros are used. One acts as a transmitter and other acts as a receiver. Next, we'll discuss on the resolvers. The construction is shown in the diagram. The inductive resolver is essentially a variable transformer with rotatory electromagnetic coupling between the primary and secondary windings. In a typical angle position, resolver windings are provided at right angles one another for both stator and rotor. The windings are located in such a manner that the output voltage has an amplitude proportional to the sine or cosine of the input shaft position of the rotor with respect to the stator. Depending upon the designer's particular applications, either the rotor or stator may be used as a primary. The advantages of synchros and resolvers are high reliable, high accuracy with 0.01% feasibility, infinite resolution, useful operating angle of 360 degrees and capable of continuous rotations, no rotational wear, expect at slip rings, relatively insensitive characteristics to stray cable capacitance. The operational speeds of the systems are quite high. Next, we'll discuss on induction potentiometers. So these are linear synchro devices which provides an accurate linear indication of the shaft rotation about the reference position in the form of polarized voltage whose magnitude is proportional to the angular displacement and whose phase relationship indicates the direction of the shaft rotation. The arrangement is shown in the diagram, which consists of a rotor and the stator with angle of theta. It consists of a rotor attached to a transmitting shaft on which the primary is wounded and its stator is wounded with the secondary winding. The winding designed so that the output voltage is directly proportional to the angular position of the rotor. A linearity is feasible for the angular displacement in the range of plus or minus 45 degrees only, even though the shaft rotation is continuous. The error can rise due to the following mechanical asymmetry, variable output impedance, and thermal effects. So these devices are analogous to the resistance potentiometers, but since they are induction type components, they have less restraining forces acting upon the rotors and hence are capable of providing the higher resolution. Next, we'll discuss on MEMS, micro electromechanical systems. MEMS are small integrated devices or system which is combined electrical and mechanical components like microsensors, microactuators, and signal transduction elements. This system ranges a sub-micrometer to a millimeter level and can be fabricated from few milli to a particular system. The elements of MEMS interfaced with electronic and non-electronic signals. MEMS are used to sense and control active mechanical process on micro scale and function individually or in arrays. The advantages and applications of MEMS. The advantages are better stability and higher accuracy in performance. Can be produced on mass scale once the fabrication design and process is finalized. Available in very small sizes, they can be easily inserted with the other applications. Compact integration of comprehensive functionality. Depending on requirements, the MEMS can be designed for various signals. Examples like mechanical, optical, electrical, and biological, etc. And the applications are consumer products, process and manufacturing industries, aerospace industries, automobile engineering, in telecommunication engineering, and in medical fields. The construction of MEMS. The diagram shows a general representation of MEMS consisting of input signals. So these signals are received from various sources, systems such as mechanical, electrical, optical, chemical, etc. And MEMS package consists of the following elements: microsensor, sensing the element, sensing processing hardware, etc. And the sensor senses the physical parameters such as temperature, force, humidity, sound. Micro actuating the unit commands, transduction stage, micro actuator converting a electrical signal to a physical signal, output signal. So these are the signals interfaced with the system to be controlled or monitored. Manufacturing of MEMS. The technique employed for manufacturing MEMS is called micro machining or micro manufacturing. The following are the various techniques. The first one is a bulk micro machining. So it is used for a production of microsensors and accelerometers. In this method, isotropic and anti-isotropic etching techniques are used. The surface micromachining, it is produced by the depositing pattern and touching a sequence of a thin film, typically 1 to 100 micrometer. Deposition technique used low pressure chemical evaporation deposition technique. Polysilicon is a commonly used material for depositing a layer. The next one is LIGA process, lithographite galvanoforming form. In this technique, a thick microstructures having a flat and parallel surfaces are produced. The process involves the following major steps: deep X-ray lithograph, photoresist with desired pattern, and electroplating. It is widely used to produce the micro gears and micro turbines. Applications of MEMS are MEMS accelerometer vibrating microsensor. The vibration analysis is useful method to observe the rotating machine performance, and it is measured by the frequency and amplitude of vibration. The most common type vibration sensor is accelerometer. The accelerometers are designed for a purpose of measurement of the shocks and vibrations. The piezoelectric type accelerometer has the highest frequency response and high output voltage, making it convenient for measurement of shock and vibration. Most suitable piezoelectric material for fabrication of MEMS accelerometer is lead zinc nitrate oxide. Electric sensor is a self-generating device which has a ideal for sensing dynamic events such as shocks and vibrations. And the following are the advantages of ZT sensor: the fast response, better stability, high frequency bandwidth, and high sensitivity. The construction of ZT is shown in the diagram. A membrane of silicon wafer with SO2 layer is fabricated by bulk micromachining. The film of PZT is sandwiched between the platinum electrodes by depositing technique. The accelerometer is connected with the vibrating surface. According to the working principle, the PZT film experiences a force and an electric charge is developed across it, and this charge vibration can be converted to voltage variation of the output by charge amplifier. The applications can be given as suited for Z measuring and analysis, the vibration levels at rotating machines, pumps, compressors, and turbines. So these measurements may be useful for controlling the vibration to check noises and damages for rotating machines. So next, a MEMS humidity microsensor. Diagram shows the construction of humidity microsensors. For such sensor, a barium trinitrate BaTiO3 is used because it undergoes the strong changes in dielectric constant when exposed to a humid atmosphere. The BaTiO3 is a synthetically produced piezoelectric material, ferroelectric ceramic, has a high permittivity with a good used polarization. It is conveniently used in the sensor. The advantages are good mechanical and thermal stability, good frequency response sensitivity, and large dielectric constant. Thank you for watching, and please subscribe to our channel and hit a like button.